So good morning, students. So today I'll take up a topic called friction. So I have discussed about the friction in the previous class also about the definition. So today we'll see what are all the types of friction. What are all the types of friction? See, as you are all aware that the friction creates a wear, and this wear is nothing but loss of material due to friction. So friction can be classified as static friction, rolling friction, kinetic friction, sliding friction, and fluid friction. So these are all the major classification of friction. We'll see those frictions so one by one. So first one is the static friction. This static friction occurs when the two objects are not moving relative to each other. So best example is a desk on the ground. Say desk is stationary and the ground is also stationary. So the desk is on ground. It is due to purely due to the friction between the desk and the ground. So this kind of friction is called static friction. The coefficient of static friction is typically denoted as mu. That is the Greek letter mu. And the initial force required to get an object moving is often dominated by static friction. So next one is rolling friction. This rolling friction occurs when two objects move relative to each other. So that is one object rolls on the other one. Best example is car's wheels on the ground. Okay, so the wheel is rolling and the ground it is stationary. So this kind, the friction induced due to this is called rolling friction, and this is also classified under static friction because see that the tire is rolling whereas the ground is stationary. Okay, this can also be treated as static friction, but since the tire is rolling, so you can call it as rolling friction. Another one is the kinetic friction. It occurs when two objects are moving relative to each other. So whereas in case of rolling friction, one object is rolling and the other one is stationary. Whereas in this case, that is kinetic friction case, so both the objects are moving relative to each other. Okay. Uh, and the coefficient of kinetic friction is typically denoted by mu k. Mu k refers to kinetic. In this case, mu s refers to static. Mu is it's a coefficient of friction, Greek word. S stands for static and K stands for dynamic. Okay. And the sliding friction, it occurs when the two objects are rubbing against each other. So sliding. So just take an example of your palm sliding with each other. Okay. So putting a book flat on the desk. So just keep a book on the desk and just slide it off. The friction is created. So that kind of friction is called sliding friction. And the last one is fluid friction. So fluid friction, it is a friction between a solid object as it moves through a liquid or gas medium. And the drag of air on the aeroplane, it is also again a fluid friction. Say aeroplane body is a solid one. So it has to fly over the sky. So air drag will be there. And this air drag creates a friction. We call it as fluid friction. And also when you swim in the water, so the water, it's a fluid. Fluid is basically, it's a common term used to denote liquid and gas both. So when you swim in the water creates some sort of resistance to flow. So that is called fluid friction. These are all the best examples of fluid friction. Next, and this friction is important to keep us walking, driving, And this, as I said earlier, friction is a necessary evil. Okay, sometimes friction helps us, and sometimes friction creates a problem. So it has got two contribution, good and bad. So since it can damage just the device
Excuse me, sir.
and is the reason for where it is said that half of us all energy is produced is spent to overcome some type of friction. Then because of the friction, the material loss takes place. We call it as wear. So we have adhesive wear. Many types of wears are there, among which the adhesive wear is very important. We can classify the wear into adhesive wear, abrasive wear, phoretic wear, like that. But
Excuse me, sir.
ah,
Sir,
what
allow
happened?
ಮಾಡ್ಬೇಕಂತೆ ಸರ್ ತುಂಬಾ
See,
ಜನ
I
ಇದಾರೆ, allow
cannot allow
ಮಾಡ್ಬೇಕಂತೆ.
all these guys. The time is already 11:25. Don't entertain them. Okay.
ಓಕೆ ಸರ್.
So I have, see, from next class or next class onwards, I will allow them up to 11. Suppose if the class starts at 11:15, I'll allow them up to 5 minutes. 11:20 is the last. Further, I cannot allow them because it distracts me a lot. If I keep on admitting them, it will hamper my presentation. That is the reason. Okay.
ಎಸ್ ಸರ್.
Uh, so then lubrication. See, lubrication refers to the actual action of rendering something smooth or slippery. So lubrication occurs when opposing surfaces are completely separated by lubricant film. The applied load is carried by pressure generated within the fluid, and the friction resistance to motion arises entirely from the shearing of the viscous fluid. We have discussed about the lubrication in the previous class also, and we have I have discussed about various types of lubricants: solid lubricant, liquid lubricant, semi-solid, semi-liquid, like that. We'll see what are the types of lubrication. See, when it comes to lubricant, we have three types. Three terminologies, especially related to this: lubrication, lubricant, and lubricators. Okay. Hello, is it visible, the presentation? Can anyone reply to me?
Yes, sir.
Okay, fine. So I had some technical problem.
ನೋ ಸರ್.
Is this PPT visible to you? Hello?
Yes, sir.
Oh, okay, fine. Lubrication. Okay. See, the terminologies lubrication, lubricant, and lubricator. So understand it first. So lubrication is it is a process of applying a lubricant. Lubricant means it is an unguent, a substance which is applied over the surface. Lubricators are the devices used for lubrication. So last class I have discussed about the types of lubricants. today I'm going to discuss the types of lubrication process. Process of applying lubricant on the surface is called lubrication. So three important lubrications process are there. One is hydrodynamic lubrication, hydrostatic lubrication, and elasto-hydrodynamic lubrication. So hydrodynamic lubrication means the load carrying surface of a bearing are separated by relatively thick film of lubricant so as to prevent metal to metal contact, and that the stability thus obtained can be explained by the laws of fluid mechanics. So best example is journal bearing. See, in case of journal bearing, basically it consists of two components. One is journal, nothing but a rotating shaft, and it is housed with the bearing block. So in between journal and the bearing block, so lubricant has to be introduced, okay, a liquid lubricant. And when the journal starts rotating at some RPM, some kind of hydrodynamic action takes place between the journal and the bearing block, I mean the shaft and the bearing block, and that hydrodynamic action is sufficient to lift the journal and which rotates at higher RPM, and this kind of lubrication is called hydrodynamic lubrication. It is called hydrodynamic lubrication. And next one is hydrostatic lubrication. So hydrostatic lubrication, normally it is observed in thrust bearings. So vertical bearings, thrust bearings. So in case of hydrostatic lubrication, a lubricant is supplied to the bearing by means of external pressure. Okay, some pump through the supplying pump, lubricant is supplied into the bearing, and that bearing carries the journal which is in the bearing carries the load, and as soon as the load increases, you have to increase the supply of the lubricant. So in order to balance, in order to withstand the load. So this kind of lubrication is called hydrostatic lubrication. Okay, and this hydrostatic lubrication is obtained by introducing a lubricant, which is sometimes it can be an air or water or some lubricants, liquid lubricants, into the load bearing area at a pressure. So this is very important. At a pressure high enough to separate the surface with a relatively thick film lubricant, so that the journal is lifted. And whereas in case of hydrodynamic lubrication, so you need not to supply the lubricant by means of by externally. So whatever the hydrodynamic action that is being created between the running shaft and the bearing block, it is enough to lift the journal. Okay, and elastohydrodynamic lubrication, it is the phenomena that occurs when a lubricant is introduced between the surfaces.
Okay.
Huh? Hello, that are in rolling contact. Okay, elastohydrodynamic lubrication. Elastohydrodynamic lubrication is used in case of lubricant, in case of rolling bearings. And the mathematical explanation requires Hertzian theory of contact stress and fluid mechanics. You need not to focus much on this elastohydrodynamic lubrication. So our study is restricted only to hydrodynamic lubrication and hydrostatic lubrication. So you are going to study more on this hydrodynamic and hydrostatic lubrication in the subsequent modules, coming modules. So there is a separate module dedicated to hydrodynamic lubrication and one more module dedicated to hydrostatic lubrication. This elastohydrodynamic lubrication, it is observed in very few cases. So you need to learn about the Hertzian theory for understanding this. So for your syllabus, you need not to learn about this. But in order to know what are all the basic, what are the types of lubrication. So if you get a question on this, so just explain this. What is this? What is this hydrodynamic lubrication and hydrostatic lubrication and elastohydrodynamic lubrication? Next topic is viscosity. So more oftenly you have heard about this viscosity in fluid mechanics, and in many topics related to fluid. Say this viscosity, it is a measure of fluid as a resistant to flow. So normally fluids flow. Viscosity, it is a measure. It is a measure of fluid resistance to flow. So I'll just explain this viscosity with a neat figure over here. So consider this diagram. There are two plates. The bottom one is a stationary one, and the above one is a moving plate. Okay. So in between this surface is filled with a lubricant. This surface, this portion is filled with a proper lubricant, and a force is being applied to the upper plate, and this plate moves with velocity u. This plate moves with velocity u, whereas the bottom plate is stationary. And H is the film thickness, I mean the lubricant thickness, and Y is the location of lubricant. I mean your the observing point of interest. So you are finding the velocity of the lubricant at a distance y from bottom plate. So like that, if you want to find the velocity of lubricant at this portion, so this y goes to that level. So like that, and u is the velocity of flow. Okay. So considering this diagram, I'm going to explain the viscosity. So figure 1, let A is a moving plate with a velocity u on a film of lubricant thickness h, and we imagine that the film is composed of series of horizontal layers. See what happens when you observe a fluid flow, the fluid flows layer by layer by means of shearing action. Look at this. This fluid particles flows layer by layer due to shearing action. Okay, the particles which are associated with the upper plate, I mean the moving plate, moves with a higher velocity, and this velocity slowly comes down, and the particles which are associated with static plate, I mean the bottom plate, will have zero velocity. Okay, like that the velocity slowly increases, gradually increases from point to point, and the particles which are associated with moving plate will have maximum velocity. That you should understand, and that is being stated over here. Say according to Newton, say Newton, one who postulated various forces theories, Newton's law, first law, second law, third law, like that. He also demonstrated the mechanics, fluid mechanics. Okay, so according to Newton's viscous effect, states that the shear stress in the fluid is proportional to the rate of change of velocity with respect to y. So according to Newton's law of viscosity, the shear stress in the fluid, that is tau. Shear stress means tau. Normal stress means sigma. Shear stress in the fluid is proportional to the rate of change of velocity with respect to y. Y is point of interest from the bottom plate. And mathematically, it can be expressed as tau is equal to F over A is equal to mu into du over by dy, where mu is the coefficient of friction. We'll see that expression further. So where mu is called as coefficient of friction or absolute viscosity. Okay, and also that is not the coefficient of friction, it is absolute viscosity. And the derivative du by dy is the rate of change of velocity with the distance, and may be called that rate of shear or the velocity gradient. The viscosity mu is thus measure of internal friction resistance of the fluid. So considering a du over dy is equal to u over h, where du is the change in velocity and dy is a change in that distance, height. Okay, so that can be correlated as u over h. And further substituting this into this formula, that is tau is equal to f over a is equal to mu into u over h. So extracting viscosity on the other side, you will get an expression for viscosity. Viscosity mu is equal to hf over ua, where h is the film thickness, f is the force that is applied to the upper plate, and u is the velocity and A is the area of cross section. And these fluids exhibiting these characteristics are called Newtonian fluids. Fluids can be classified as the two types of Newtonian fluids and non-Newtonian fluids. Newtonian fluids are the one which obeys Newton's law of viscosity. Non-Newtonian fluids are the one which doesn't obey Newton's law of viscosity. And the unit of viscosity in IPS means inch per second. Okay, system is seen to be pound for second. So anyhow, we are not using this IPS system. We use SI system, that is Pascal second. The unit of viscosity is Pascal second in SI system. So Pascal means Newton per meter square. So Newton second per meter square, you can call it as nothing but Pascal second. And one more topic, that is effect of temperature on the viscosity of the liquid lubricants. See, viscosity, it mainly depends on two entities. One is temperature, the other one is pressure. So we'll see the effect of temperature on the viscosity with the graph indicated over here. Anyhow, I'm going to provide a data handbook to you, a soft copy, data handbook soft copy, that you may have to refer it for solving various problems in case of tribology. So in the data handbook also you'll get this chart. Okay, how this viscosity is varied with respect to temperature. So just go through that. I will send you the soft copy of the data handbook very soon. Just refer it. So when you observe this graph, so this observed viscosity is plotted in y-axis and the temperature in Fahrenheit is plotted in x-axis. So I have taken various fluids. One is castor oil, the other one is SAE 30 oil. So SAE stands for Society of Automotive Engineers. So you can have oils SAE graded as SAE 10, SAE 20, SAE 30, 40, 60, 80, like that. Okay. So it is internationally accepted grade. A lubricant to be sold commercially means it has to be sold under this name SAE 2030. Brand may be different, but the specification is this. So SAE 2030, like that. We have one more specification, that is SAE 10W, SAE 20W, 30W. See, that W refers to winter. Okay. So as you are all aware that this world is can be geographically segmented. It can be segmented into two or three parts: equator region, polar region, south pole, north pole, like that. So when you go to polar region, the temperature drops drastically. So you can have minus degree also. So in that case, those countries, polar countries, they'll have different specification. Okay. So the specification is, suppose in our country, it is almost nearby to equator region. So we follow this grades SAE 30, 20. Polar countries, they follow SAE 10W, 20W, 30W. So only thing is the W means refers to winter. So some additives are added so that the lubricant should not get freezed. Okay, what happens if the temperature drops, the lubricant solidifies? No. In order to avoid that, some additives are added, some chemicals are added so that that lubricant maintains the viscosity even at lower temperature. Okay, so that is different grade. So we, the equator country, the countries which are nearby to the equator, we follow some grade. So SAE 30 is, so when the oil is taken over here, water is taken, gasoline again, and it is taken, fuel is taken, air is taken. So just observe the pattern of the graph. Okay, see, as the temperature increases, the viscosity value also increases. Sorry, as the temperature increases, the viscosity value decreases. Look at this. Viscosity is decreasing as the temperature is increasing. So like that. So it means that the lubricant which operates at higher temperature, it loses its viscosity. It becomes a thin oil, a thick oil. When you heat up, it becomes thin oil. So like that. So just take an example of castor oil. Castor oil is very thick in nature. You just heat that castor oil. So some property of the viscosity is it loses its viscosity property, and the oil becomes thin. So that is the best example. So just have this in mind. As the temperature increases, the viscosity value decreases for lubricants. So you might have seen in advertisement some renowned companies, they do advertise their products or oil products. They're quoting a word that the viscosity retains or remains even at high temperature. So that is indeed needed for a lubricant if it is used in heat engines. Normally, heat engines, when it is in running condition, the temperature increases. The fluid, the lubricant which is there in the heat engine, it also heats up, and definitely the viscosity comes down. So when viscosity comes down, it cannot work effectively. I mean, the purpose of lubrication. So in that case, a good lubricant should retain the viscosity even at high temperature. So for that reason, they add some additives anyhow. So that is the indeed requirement. And we have one derivation related to this. So that is flow between the two parallel stationary plates. Okay, how this fluid behaves when it is flowing through stationary plates. So I'll just consider this derivation. So considering a fluid molecule over here, a rectangular block, fluid molecule is taken, and this is the distribution, pressure distribution, how the pressure is being distributed. So this is one plate and the other one, this is another plate. Both plates are stationary, but the fluid is flowing in between the stationary plate. So I'll just, for the derivation purpose, I will take a unit molecule having dimension 2y here, breadth B, height 2y, and the pressure P on left side. When it comes to right side, the pressure is dropped. It is dropping by value of dp. So net pressure is dp minus dp, and t is the distance between the upper plate to the center of the axis center, and tau are the shear stresses induced against the fluid flow. This is tau on the other side. On both sides you will have two surfaces, means two shear stresses, and dx is the length of the molecule, and b is the total length of the plate. Okay. So the equation of the equilibrium forces acting on the element of fluid having the thickness 2y and the length dx and the width b is given by. So first I will consider the pressure force acting on the left hand. So this side, force acting on the left hand. So P, we know that pressure P is equal to force by area. Then the force is equal to pressure into area. So this is pressure is P and the area is 2y into B. 2y into B. So I'll consider this. Force acting on the left hand is pressure into area. Similarly, force acting on the right hand is pressure into area. So the pressure on the right hand is P minus dP, and the area is same, 2y into B. So shear force. So shear force on the upper side and the lower side. Both side will have shear force. Shear force is also the same. Shear force, shear stress. Shear stress is equal to shear force by area. Then shear force is equal to shear stress into area. So considering that two, since it is acted on two sides, I'll take up two. So then applying the law of equilibrium, sum of all the forces acting acting at a point is equal to 0. That is sigma f is equal to 0. Considering all the forces which are acting rightward positive and the forces which are acting leftward negative. So taking that sign convention, I am going to establish an equation. So the equation comes here, P into 2yb, that is, this is the force acting the right side, and this is the force acting left side, and the shear stress. Shear stress is induced against the direction of the rate of flow rate. So minimizing this equation, I'll get dp is equal to tau over y into dx. So again, further minimizing, further simplifying this, dp by dx is equal to tau over y. So we have seen that according to Newton's viscous law, tau is equal to mu into du by dy, or you can introduce a negative sign because the shear stress is induced opposite to the direction of the fluid flow. So this negative sign indicates that, and in this case the velocity u decreases gradually as the y increases. So look at this. As the y increases, the velocity u decreases in the here this case. Okay, finish. Oh, okay. Using that relation over here, here. So I'll get the expression for dp, and also I'll just rearranging this, I'll get the expression for du. So where dp by dx is the pressure gradient. Okay, so this dp by dx is the pressure gradient. So just rearranging that, I'll get the expression for du. So now integrating the above equation with respect to u, this equation. So I'm going to get the velocity. So this is integration, keeping the constant term on one side and the variable within the integration. So just go through this. So just a purely mathematics and applying the boundary condition. U is equal to 0, then y is equal to h by 2, nothing but t here. So h by 2 means nothing but t. Okay. Then simplifying this, putting that u value 0 and extracting the constant c1 over here, and again resubstituting back into this equation. So I will get the expression for u, that is velocity distribution across the plates. And it is observed that this velocity is distribution is parabolic in nature. So t square minus y square, this indicates parabolic in nature. And also you can find out the maximum velocity. This maximum velocity occurs when y is equal to 0. So when y is equal to 0, you'll get the expression for maximum velocity. So just to substitute this y is equal to 0 into this equation, so I'll get the expression for maximum velocity, that is u max. So it is simplified as u max is equal to h square by 2 8 mu into dp by dx. So with the use of velocity, I can find out the rate of flow. So using this expression, the flow rate q is given by u into dA, that is velocity into area. So area is dA is equal to 2b dy, and this dq is equal to 2 into u dv dy. So you can have this expression dq. So differentiating this, I'll get the expression for dq. So with this, we have derived expression for velocity and flow rate in case of fluid flow between two parallel plates by considering Newton's law of viscous flow. Clear? So this is all about viscosity. So in today's class, we have discussed about the various types of lubrication, and then we understood what is viscosity and Newton's law of viscosity. And with the use of Newton's law of viscosity, we have derived an expression for velocity distribution and flow rate distribution in case of rate of fluid flow between parallel stationary plates. Okay. So with this, I'll end up the session. Next class, I will take up the other topic. Okay. So thank you. Thank you, one and all. Put your USN in the chat box.